Hi. This lecture about planar kinematics of a rigid body. So first we have to distinguish between a rigid body and a particle, because I believe that I found some confusion about how we can define a body is a rigid body or a particle. Well, somebody said, okay, if it's really small, if the body is small, we can consider it as a particle. Well, I will say that's not really the correct answer, because the size, small or big, it's relative to the analysis what we're going to do with this object, right? So particle, for example, the dimension, yes, insignificant, but the dimension is irrelevant to the description of its motion. That's when we consider it as a particle. For example, if we have to study the aeroplane flying from one state to another, and we are following the path of the aeroplane, and as tracing the path and discussing the kinematics of the aeroplane path only. So in this case, the aeroplane we can consider as a particle. All right, and the same object, the airplane, if we are going to study the rotation about one of the axes of the airplane, in this case, the dimension is important in studying the same airplane. So in this case, we cannot consider it as a particle, but we are going to consider it as a rigid body. Okay, first we will say that because as a body, not a particle. When you add the word rigid, it adds another property for the body, which is, you have here in the picture, just a simple thing. The rigid body that will not suffer from deformation when forces apply to it, but the one here to the right, it's not rigid, because deformation can happen when the force affected. So we are going to study kinematic for rigid body. So it means that the dimension is important for us and it's rigid. So we are going to ignore any deformation, or when the deformation is insignificant with respect to the dimension and the size of the body. So it's a rigid body. Okay. Well, the planar motion now we are going to study motion or rigid body and planar motion. Planar motion, it means when the rigid body is moving in a plane on a page. You have X and Y. That's what I mean. All right. What are the types of planar motion we are going to study? There are three types. The first one is translation. The second is rotation about a fixed axis. And the third one, general plane motion, that include the previous two types of motion. Let me just show you some diagram that it explains in more detail so you can visualize what does it mean. For example, if you have a body here, rigid body here, this one, and you trace 3 points, A, G, B. G is the center of gravity, A and B another 2 points. So if this rigid body move in this direction, you will find that the 3 dots here, or the 3 points on the points, if you connect them by the all of them will be parallel straight lines. So it means that the rigid body is translating, or the translation, vectorial translation, can describe the motion of this rigid body. Rigid body doesn't have to be in a straight line. It can be curvilinear. Like if you have you have again 3 points here on the body. Of course, all the points. I'm just giving an example. If we trace the 3 points, and when this body move in rectilinear motion, and find that all curvilinear translation happens from point A to the new point A after it moved this distance, you find all of them, they are parallel to each other. So that's the curvilinear translation. So both describe the translation. One is rectilinear and the second is curvilinear. Now, and of course, there are examples like for rectilinear translation, you can look at the rocket test sled here. It's moving, the whole rocket moving from one point to another point. You'll find all points on the body. After the translation, you'll find if you connect the old and the new point, you will see that they are straight lines and all of them are parallel to the direction of motion. For curvilinear, it's like you have here a parallel link swinging plate, and when swing, you will find that this point, for example, and if you look at this point, it in this position. After it move, it will be in different position. So you will look at the line that move, and you look another point, you'll find it's just the same parallel curvilinear translation. So these are the two types of translation. Now we'll go for rotation about fixed axis. This thing represents the object or the rigid body, and it's swinging about the point O. So you'll find that first of all, the point that's swinging, it's fixed. It's not changing. Its position not changing. This point, and then if you trace it like part of a circle here, so that will be considered as rotation about the fixed axis. And we have many examples like simple pendulum, for example, or compound pendulum that represent rotation about the axis. Okay. The last one will be like general plane motion, which really most equipment or tools, devices, they really apply the general plane motion, that they have both. It's a combination of translation and rotation. So the translation occurs with a reference to the plane. So you have the 2 points A and B. They will go to A dash and B dash. So it's not just translating, it's translating and at the same time also rotating about a fixed axis. And that's an example. Actually, I have a very good practical example that maybe you guys have idea about it. So that's the general plane motion example. If you look at this link, all right, it's rotating. And if you look here at this wheel, it's also rotation about fixed axis. This is the fixed axis where the rotation happened, and that's the fixed axis where this wheel is rotating. However, this link have a curvilinear translation, all right? So in the end, you have general plane motion. This one will be rotating and also translating from one point to another. So that's like combination of both rectilinear translation and rotation about fixed axis or fixed point. So the first one is the translation motion. We are not going to talk about a lot because I think we did rectilinear motion before, and just so I will just go ahead and go for rotation about a fixed axis. That's we want to focus today's lecture on this one. Okay. So in this diagram, you can see that this is the rigid body here, and this rigid body is rotating about this point, this axis, the vertical axis. And if you look in the top here, you can look at the top view. If you make like a section, cross section here, you look at this and bring it here, that it look like a circle, right? So if you look at the point P, what's point P? It's just one point. You can choose any point on the circumference of this circle or this disc and follow what's happening to it. Measure the angle from any reference you choose, and that's the reference we are going to choose from the. Here you go in the big picture. I'm choosing this reference. You can choose any reference, but just you got to have a reference so you can measure the angle of rotation of any point that you pick on this diagram. So it will move, it will make an angle theta, and angle theta that will be called the angular position and is measured from a fixed reference line R. So this is the reference line R, all right? And of course, if you have, if you want to measure the increment of the angular position delta theta, and its direction will be always along a fixed axis. So you can say that if you look here at if you just curl your thumb here and around the direction of motion, and this is the direction of the motion here, and that will be the axis that you are rotating about. So the direction is determined by the right hand rule. If you know the angle and you can measure the time, what I mean by this, let's say that you move to 30 degree, and then just to increase it a little bit, let's say delta theta is like 2 degrees, and then count the time. Let's say that if you have really precise time, 0.2, then you divide the increment of the angle by the increment of time, you can get the angular velocity. So the angular velocity here, it's equal the rate of change of the angular displacement with respect to time. That's called the angular velocity. All right. And at the same time, if you find the first derivative of the angular velocity, you can find the angular acceleration. By the way, that's not strange because we did that in translation. Like when you have the translation of something moving along x-axis, all right? So if you want to find the speed, you say v is equal dx by dt. That's the velocity. That's the linear velocity. This is similar to this one. This equation is similar to this equation. The only difference, just to replace x by theta. That's rectilinear motion. So x is like along x-axis. Theta, that's the angle about some point that where it's rotating. So this is the increment of angle. That's where you find the angular speed omega instead of finding v. So v is the linear velocity and omega is the angular velocity. And the acceleration, how you find the acceleration in rectilinear motion, you just find the derivative of the velocity. You say dv by dt. It's the same thing. If you want the acceleration, the angular acceleration, you just find the first derivative of the angular velocity. So they are so similar in the sense of how to find the velocity and the acceleration. Great. So again, similar to the rectilinear motion, if you have constant angular acceleration, if you remember, if you have constant acceleration or constant rectilinear acceleration, it's called also AC, constant. I will just drop C, subscript C to make it easy. What do you remember? We say X, velocity is equal initial velocity plus acceleration times time. That's what we learn in rectilinear motion. The same thing here. You have here the angular velocity is equal the initial velocity plus acceleration. That's why we write acceleration as alpha, but in rectilinear motion write just a, lowercase a, times t, the same thing. And also we said that if you want to find the displacement, delta x, we said that's equal the initial velocity times plus 1/2 at squared. And what's delta x displacement? It's the final position theta minus initial position x naught. So, and it's the same thing here. If you just remove theta naught in this one, you will have delta theta is equal to the initial angular velocity plus 1/2 acceleration t squared. And the same thing for the third equation. You have also in direct, remind you by direct linear motion, v squared is equal v initial square, initial velocity square, plus 2a acceleration time the displacement delta x. It will be the same thing for constant angular acceleration. You will have the final angular velocity square is equal the initial velocity square plus 2 acceleration time the displacement, angular displacement. So they are so similar, but we don't use this set of equations, but when only constant angular acceleration. So actually it's very similar to what we use these equations in general, the omega equal d theta by dt, and here I will give you like the equation in vector form, but we don't use it except only if we cannot visualize the picture of motion. So we'll use the mathematical expression just like that. But I believe that it will be, you will not have problem to use the normal equation. Let's just go through one by one. I'm explaining here the rotational motion about fixed point O, as you see here in this picture. So what is vector R? Vector R, it's the position vector from the point of rotation O, and P is a point on the body, rigid body, where it's moving. The whole body is moving, by the way. So just I'm taking one section. So this point P is moving. So R is the position vector. It's measured from the point O up to the point P that's located on the rigid body. Okay, so and how you the displacement, you can of course measure the displacement by measuring the angle that it moves and multiply by the radius. I wanna tell you why. If you have a circle, and let's say that this is the point O where it's moving, and this is the point B. And let's say that this particle, or the whole thing, move like that, so this point come here, B dash. So, and by the way, let's just tell you, this is the position vector R, measured from the origin O to the point B. So it made an angle delta theta. And this angle I'm talking, it's a very small angle. So we need to find this displacement. It's equal to the length of the arc. How to find the length of the arc? All right. To find the length of the arc, that's the arc length. That's equal to the radius, which is R, times the angle d theta. It gives you this ds. That's how we find the displacement, or the length of this arc. The radius times the angle. But this is only applicable when the angle is really very small. And there is a reason for that. Because you can imagine this if you make like a tangent. So the tangent will be almost equal to the arc. So if you make a tangent at point B and you have a right angle triangle, you can think about it as a right angle triangle. So, and this is R, and this is delta theta. Make it delta theta. So this will be what? R sine delta theta. So that's equal to R sine delta theta. But when the angle is really small, in this case, sine delta theta will be equal delta theta in radian, not in degree. Very important. So when you apply this rule, delta theta is measured in radian, not degree. And since this tangent that we did is really its length very close to the arc, so just we can make it approximation, it's equal to R delta theta. So that's how we find ds. That's how we got this one. About the velocity of the particle, which is the tangent to the path of the motion here, or the circle, it's moving along the circle. If you want to find the velocity of this point, you make the tangent to it. So this velocity is equal to the angular velocity times the radius. That would be times the radius. Okay. Well, why? Simply, it's ds is equal r d theta, which is proof. This is the displacement is equal r d theta. If you differentiate that with respect to time, so that will be the velocity, and that will be the angular velocity. So the linear velocity is equal the angular velocity times the radius. What is the radius? The radius, it's the radius of the circle motion that's doing, or the rotation. So v is equal omega times r. All right. If you, of course, this is easy to use. We used a lot. The velocity is equal omega times r. But when you have 3 dimension, you can use the cross product of omega times r to get the magnitude and the direction. But remember, when you make the cross product, the angular velocity cross product r is not equal to r cross product omega, it will change this direction. So be careful of the order. Omega first, the cross product r. That will give you the magnitude and the direction of the velocity. Now let's go for the acceleration. The acceleration of particle B, it consists of two components. The first component is the tangential component and the second is the normal component. How to find the tangential component, as we did on other application in previous chapters, by finding the rate of change of the velocity with respect to time, dv by dt. And since we know the velocity is equal to omega times r, so you replace velocity by omega r and find the differentiation. The radius is constant, it's fixed here in this diagram. To get it outside here, so what's left, d omega by dt, which is equal to the angular acceleration alpha. So actually the tangential component of the acceleration is equal the radius times the alpha times the angular acceleration. If you want to use it mathematically, if you have 3 dimension, so the cross product of the angular acceleration cross product with the r. All right. Just I want to remind you, when you did the velocity using in 3 dimension, it's equal what? It's equal the angular velocity cross product with r. This is the acceleration cross product r. So always r comes second. Just keep in mind that. All right. Now what about, we did already the tangential component of the acceleration. What about the normal one? Well, the normal one, which is directed toward the center, because I want to just you understand what does it mean, the tangential acceleration and the normal acceleration. If you see the particle here and moving along this path, so that will be the tangential acceleration, and that towards the center will be the normal acceleration. Okay, so the normal acceleration, how you get it, as we did previously, by the square of the velocity, linear velocity, divided by r. We did that before. It's equal v square over r. And now we have to replace the velocity by omega r, because we know that that's what we prove. Velocity is equal omega r. So we'll have omega square r square divided by r cancel with the r square. So you have omega square r. So the normal acceleration, or the normal component of the acceleration, is equal omega square r. And you know that r, of course, is the radius of the curvature, that we can get it before. If you want to use the 3-dimension cross product, that's the way you're going to do it. Remember that omega cross product of r, we did it before, it's equal the velocity, right? That's the velocity. And this is the omega, the angular. So when the cross product of the angular velocity with the linear velocity, it gives me the normal acceleration. All right. And if you just you have an easy problem, you can just use this formula, omega square r. So that's, I think, all the formula that we need to know. And just let's go ahead and see how we apply it in practical example. Let's take this one step by step. Okay, let's just read this. Okay, so in this example, we have an electric motor here, and it's used to turn a wheel. This motor is going to turn on the wheel. This motor, let me just make it better here. So this motor is going to turn on this wheel, rotate this wheel in this direction, and also it will the attached plug, it is going to also work. That's contained within housing. We have pulley one here, and connected to the motor, begins to rotate from rest. So it starts from rest. So it means it was at rest, means that omega naught equals 0, right? Theta naught is equal 0. And also we have a constant angular acceleration. Okay, that's important. A constant angular acceleration is given is equal to 2 radian per second. I wrote here 2 radian per second square. That's the angular, because it's given radian. So the angular acceleration of this motor. And the question is, after the pulley has turned 2 revolution, after the pulley is here connected to the motor, after make 2 revolutions, what mean 2 revolutions mean? That's 1 and 2. After 2 revolutions, we want to calculate the following. We want to find the magnitude of the velocity of the point P, that's point P on the wheel, all right? And then we want to find the magnitude of the acceleration. So we want to find the velocity and the acceleration of point P, that's on the wheel here, after 2 revolutions, all right? We'll assume that the transmission belt that's surrounding the motor and the wheel does not slip on the pulley and the wheel, all right? So the motion completely is transferred here. So that's the example that we try to solve here. Well, let's just write the information that we need, simplified. And we are using here 1 to refer for the motor and 2 for the wheel. Just to remember that. So when we write 1, it will be for the motor. So the acceleration for the motor, it was given 2 radian per second square, and the radius of the pulley is equal 0.15 meter. And do you wanna calculate everything? Do you want to calculate the velocity of P and the acceleration of P after 2 revolutions? That's the tricky part. It's easy but tricky part. 1 revolution, it make angle 2 pi. 2 revolution, you multiply it by 2. So actually 2 revolution, it means 4 pi, right? So you can say that theta 1 will rotate twice. I'll write 2 revolution. But the 2 revolution will be, I will translate it just to make it easy. 1 revolution equal 2 pi. So it means the angle that it will rotate is equal 4 pi. Okay, just before we start. And what other information given here? R2 is given 0.4 meter for the wheel. R2 is equal to 0.4 meter. Anything else? Nothing. Okay. So let's now think about how can we solve this problem. We need to find the velocity first. We'll think about it. We want to find the velocity of point P. So how we'll find the velocity of point P? Of course, it's rotating, right? So simply we need to find omega t, omega 2. Now start thinking, how can we find omega 2? So you start to say, okay, omega 2, I can get it if I know the velocity, because we know that omega is equal V times R. So if you want to get omega 2, you got to have V2 and you have R2. R2 is given, but V2 is not given. So here we starting about the problem here. Well, how we can find V2? All right. There is something important that you should know for transmission. Transmission, it means when the motion, rotation or translation is transferred from one rigid body to another one through like belt or any transmission system. If the transmission system it's assumed ideal, and what does it mean ideal? It depends on the type of transmission. For example, in this example, the transmission belt, so we are using belt here notion, does not slip. When it does not slip, it means that all the motion characteristic in the pulley and will be transferred to the wheel through this belt. What does it mean? It means that since the belt has the same speed the belt is moving with the same speed, it will transfer the speed of the pulley to the wheel. It means that the V1 will be equal V2. The velocity of this wheel at any point will be equal the velocity of the pulley at any point. They will be equal. So through this belt, we can say that a transfer velocity means V1 will be equal V2. Not only that, even the tangential acceleration, because the belt is tangent to the wheel, tangent to the pulley. So I can also say that the tangential acceleration of the pulley, it will be equal to the tangential acceleration of the wheel. That happened because we have transmission belt that does not slip ideal. So we are getting closer, because the problem now, I don't have the velocity, so I need to find the velocity. So that's why I will let me just write what I said now. I said that the belt, the transmission has the same speed. Doesn't change speed. The speed at any point in the belt is the same, right? And tangential acceleration as it passes over the pulley and wheel. What does it mean? It means that V1 is equal V2, and the tangential, not the tangential component in both parts, they are equal. That's what I understand. All right. Well, so that's important information we have here. Then we start to think. I'm just following the strategy how we think about solving this problem. All right. Let's start from here. Okay, and then I start from V2. Then I found that V2, V. But I have to get V1. I have to get V1. So obviously I will start working on the pulley and the motor, because it has enough information. It has the acceleration, the angular acceleration, it has the radius, it has the angle, the final angle. So it has enough information to get the velocity. And then once I get the velocity at 1, I can get the velocity at 2. All right. So let's now think about how to get the velocity at 1. That's another issue that we're supposed to think about it. To find the velocity of 1, what's the relation between velocity and omega? It's equal omega 1 R1. Here you go. So I go to the problem. I don't have omega 1, but I have alpha 1. So I said, okay. So to find V1, I got to calculate omega 1, and omega 1, to find it, I have to have initial. And we know the initial velocity was 0, because it was mentioned here that the pulley 1 connected to the motor begins to rotate from rest. So from rest means omega naught equals 0. I said, okay. So now we can say I will work on getting omega 1. So I know that omega 1 will be omega initial plus angular acceleration times time. I said, okay, that now it's clear. That's from rest, and the acceleration, angular acceleration, is equal to 2 radian per second square. That's 2 radian per second square times time. All right, times time. Well, now I stuck because it doesn't give the time. So what does it mean? It means that this equation, I cannot use it. So what can I use? Okay, it's given delta 1 2 revolution, which equal 4 pi. So I have theta 1. So I need to find the relationship that has the omega, it has the displacement, and has acceleration. And we know that we have something similar that we did. So I will use this formula. That's omega 1 square is equal omega naught square plus 2 acceleration, displacement. All right, let's get each one. We have everything here now. This one is equal to 0 because it starts from rest. Alpha 1 is given 2 radian per second square. Delta theta is equal theta 1 minus theta naught. It starts from rest. Initially it was 0, but theta 1, we said that's equal to 4 pi, 2 revolution. So everything is there. So omega 1 squared will be equal to 2 times 2, which is the acceleration, delta theta 4 pi, and get omega 1 squared. That will be equal to 16 pi. So omega will be equal to square root of 16 pi. It's just right here. That will be equal to square root of 16 pi. That's equal to 7.09 radian per second. So we got the first thing, omega 1. That will solve a lot of problems. But you see how you think about it? It doesn't come just in one shot. You have to think about it, and it will lead you from one point to another. I got omega 1. Remember that I want to find omega 1 so I can use it to find V1, the velocity. So now I can write the velocity 1 is equal omega 1 R1. Omega 1 is equal 7.09 radian per second times R1. R1 is given is equal 0.15 meter. Multiplying both will get the velocity, which is equal to 1.064 and the unit meter per second. That will be the velocity V1. That will help in solving this. Remember that I found V1 because I know through the belt this motion will be transferred and V2 will be equal V1. So now I can say that V2 is equal V1 equal to 1.064 meter per second. So the result V2 is equal to 1.064 meter per second. All right. So we got the velocity of the point on the wheel anywhere. That would be the velocity. Great. So what else do we need? All right. We need to find also because to help us omega 2. We need to find omega 2. How to find omega 2? Well, if you have V2, you can get omega 2 because we don't know omega 2. We know that V2 is equal omega 2 R2. So omega 2 is equal V2 divided by R2. In this case, omega 2 is equal to 1.064 meter per second divided by R2. The radius is equal to 0.4 meter divided by 0.4 meter. You get the angular velocity of the point P on the wheel, which will be equal to 2.6, I think, yes, 5.9 radian per second. So we got omega 2. Excellent. So we did the first part. We found the velocity, the linear one, and angular one. So we need to find the acceleration. We need to find the acceleration because they ask about the velocity of the point P on the wheel, and we found both. We found omega 2. Now we want to find the magnitude and of the acceleration of the point P on the wheel. To find the acceleration, you got to have two things. If you remember, the acceleration, if you talk about the total acceleration, has two parts. It has the tangential one, it has the normal one. About the tangential is easy because we know that AT1 is equal AT2. Transfer through that. And to find AT2, I got to find AT1. Okay. How we'll do that? What's the acceleration in general? The tangential component. Okay. The tangential component of the acceleration, it's equal to the angular acceleration times the radius. If we go back to what we did, that's the relationship that we need. Okay. So, well, obviously I have to work on one because I believe that the acceleration was given here. Yes, it's given the alpha 1 is equal to radian. So, and I have the radius, so I will work on AT1. So the tangential component of the pulley is equal its acceleration times the radius. The acceleration is equal to radian per second square, and the radius 1 is equal to 0.15 meters. So multiply, you get 81, which is equal to 0.3 radian per second square times meter. And since AT2 is equal AT1, so write AT2 will be equal 0.3. And at the same time should be equal alpha 2 R2. R2 is given, so I can get alpha 2. Alpha 2 will be equal the tangential component, AT2 divided by R2. AT2 is equal AT1 divided by R2. AT1 is equal 0.3 and R2 is equal to 0.4 meter. So I get 0.75. Yes, and the unit radian per second square. And I got one component, which is the tangential. I'm sorry, I got that one. I got alpha 2. I got alpha 2. All right, but tangential I got it already. 82 it's equal 81. Let me write here on side, don't forget. 82 is equal 81, which is equal to 0.3. Okay, so that's great. What about I want to find the point itself. What I found here, I found for the belt, for the wheel. So that's what I want to find now for the point. So if we talk about the point acceleration, I got to find the normal component, tangential component. Tangential component is given. And what about the normal component? How you find the normal component for any acceleration En? Let's just remember that it's equal omega square times R. All right. So if you want to find for the second, so you got to put just 2 here. Do you have omega? So I have omega 2. I got omega 2. Where, yes, that's omega 2. Omega 2, we got it equal to 2.659. 2.659 square. And the radius is equal to 0.4. So we get the normal component, which is equal to 2.827 meter per second square. That's normal component. Now we have the normal component and we have the tangential component. To find the total acceleration A2 for the point P, that will be equal to the tangential square, the normal square, and square root. So we have, let's see what the tangential 0.75 and 2, okay. That's 0.3 square tangential and 2.827 the normal. We just got it. We'll do that square root and you just 87 meter per second square. And by this, you are done with the problem. We got both the velocity and the acceleration. All right. So I have another 2 examples to give. It's not enough 1 example, but it just took time to explain the beginning of the lecture. So let me do that in another recorded video, and I'm going to do it just in a second, but let me upload that. Okay, and thank you.